Hi folks, today we continue talking about polynomials, and specifically today we are going to be factoring. We're going to be starting to factor by taking out the GCF, and we're also going to be talking about difference of two squares today. So the essential question, since we have two topics, we have two questions. The first one is, how do we factor out a GCF? And the second question is, how do we factor using difference of two squares? Okay. So let's start out with answering the first question. How do we factor out a GCF? Well, it might be a good idea to talk about what a GCF actually is. So when you're finding the GCF, you're finding the greatest common factor. So greatest meaning biggest, and common meaning what everything shares. So the greatest common factor is the largest number that all the coefficients will have in common. Check for the largest exponent also that each variable has in common. So we're trying to look for the biggest things that these terms have in common. To factor, you're going to divide each of the terms by the GCF. So by whatever you decide is the largest thing that all of these terms have in common. The first term does need to be positive, so keep that in mind whenever you're dividing out what you think is the GCF. So you're going to put it in the form like this. You're going to have the GCF sitting out here in front of parentheses after you divide it out, and then whatever's left over is going to be in these parentheses. So let's talk about number one. I want to factor completely. So it's a binomial. Go ahead and move this up. There we go. Number one is a binomial. I know that because bi means two. And this has 1, 2 terms with a subtraction sign in between. So I want to look to see what the biggest number is that the coefficients can be divided by. So the coefficients are 15 and -9. Both of those are divisible by 3, right? This is divisible by 3 and 5. This is divisible by 3, and I guess 1 and 9 if you want to include those. But both are divisible by 3. And this doesn't have a variable with an exponent, so all I really have to worry about are the coefficients for this one. So I'm going to divide out each term by what I think is the GCF, which I think it's 3. And I'm going to put in the form GCF sitting out in the front. And then in parentheses, whatever is left over whenever you actually do that division. So this will still be an x squared term, but 15 divided by 3, when I divide out the 3, I'm going to be left with a 5x squared. And then when I take -9 and I divide out the 3 and bring it out in the front, what's going to be left over is a -3. So this is what I get when I factor out my GCF. So what I'd like for you to do is look at number 2, just at the coefficients for right now, and look to see what both of those coefficients are divisible by and what the biggest number is that they're divisible by. So the coefficients are 5 and 10. Both 5 and 10 are divisible by 5. So 5 is going to be part of my GCF. Now, the next thing that I need to look for that I didn't have to worry about over here, because there was no x or x squared here, is I need to check for the variables and their exponents. This is m squared and this is m to the power of 1. That means that they all terms have at least m to the power of 1. This has m to the power of 2, but they at least have 1 m. So that's going to be part of my GCF. And I'm going to write in the form GCF outside, so 5m, times what I get whenever I actually divide by 5m. So in the first term, 5 divided by 5 is 1, so it goes away. M squared divided by m, it's kind of like I'm taking an m out. so what's left over is just m. You can also think of it as exponent rules, and that exponent rule that you talked about last year was that if you have m squared over m to the power of 1, that's m to the power of 2 minus 1. Do you remember that? So this first term just becomes m to the power of 1, or m. Plus, let's talk about that second term. 10 divided by 5 leaves me with 2. If I had an m, but I divide out an m, then there's nothing left over. It's really like 2 times 1. That's still just 2. So this is my factored form after I factor out my GCF. So these aren't really that difficult. Once you start practicing more of them, the binomials are pretty basic. This is also a binomial, but it does look more complicated, and that's because there's more variables in each of your terms. So we've got coefficients, 8 and negative 12. We have A's and B's and C's. So what I'm going to do is I'm actually going to write this. I think I'm going to write it. I think I'll have enough room. I'll go ahead and write it underneath. So I'm going to take this and I'm going to expand so that you can really see all the pieces of this term. So the coefficient is 8. A squared means A times A, right? And B squared means B times B. So that first term, 8A squared B squared, is really 8 times A times A times B times B. So those are all the pieces that make up that first term. Minus 12 times A times B cubed, which means B times itself 3 times, times C squared. So times C times C. So there's that second term expanded. Now when we talk about GCFs, what we're trying to do is we're trying to take out the common things, the most common things that you can take out. So I know that 8 and 12 are divisible by a lot of things. They're divisible by 2, but an even larger number that they're both divisible by is 4. So that's going to be part of our GCF. I notice that for the variables, each term has one A. This one has 2 A's, but this one doesn't. So you're trying to figure out what each term can give up. Well, each term can give up an A. Each term can give up a B. Each term can give up a second B. But then that's it, because this term has B and C and C, and this term doesn't have anything else to give up. And they have to give up common things. So what I'm going to do is I'm going to divide each term, and I could have divided like the original terms, and that's fine. I'm going to divide each term by what I think the GCF is. So I think the coefficient of the GCF is 4. I think there's an A in there. And I think there's a B and another B in there being multiplied together, so a B squared. So I'm going to pull 4AB squared out to the front, and I'm going to leave some space for what I think is left over once I divide. So 8 divided by 4 is 2. A over A, those will go away, but I still have an A there, so that shows up in my term. And then B times B is B squared, but I'm dividing by B squared, so I'm taking that out, and there's nothing else in that term. Minus 12 divided by 4 is 3. I've got an A and an A that I'm taking out. I've got B times B, which is B squared on the top and B squared on the bottom, so that goes away. But then I've got this left over, so that's going to remain in my term. And then C times C is really C squared. So I'd like for you to pause your video and try number 4. So on number 4, coefficients are 6, negative 9, and 3. All of those numbers are divisible by 3. I look at the W terms. This has 2 W's multiplied by each other. This has 3 W's. This has 2 W's. So each term has 2 W's that they could give. They don't each have 3. Only this one has 3. But they all have at least 2 they could give. And for the Z terms, this is Z squared, Z, and Z. So they each have at least a Z that they could give up to the GCF. So when I divide, 6 divided by 3 is 2. W squared over W squared cancels out. And Z squared divided by Z leaves a Z. Next term, negative 9 over 3 is negative 3. W cubed over W squared, 3 minus 2 is 1, so there's just W to the power of 1, and then the Z's cancel out. And in the next term does not go away and become 0. Even though 3W squared Z is on the top and the bottom, what do you get when you divide 3 by 3? You don't get 0. 3 goes into 3 how many times? 1 time. W squared goes into W squared 1 time. Z goes into Z 1 time. 1 times 1 times 1, that's 1. So make sure that you don't just cancel that out and make the term go away and become 0. It's still 1. So you have numbers 5, 6, 7, and 8 to do. I'd like for you to pause your video, try it out, and once you come back on, then you should be able to check your answers with mine. So take a moment to check your answers for 5, 6, 7, and 8. If you made a mistake, totally fine. It's your notes. This is where you learn from your mistakes. So try to look at the work that I have and the work that you have, and let's see how they're different. Some things I want to point out is that these 4 examples are designed to teach you a few things. Let's work backwards. Number 8 is designed to show you that you can do this with more than just numbers and variables. You can do it with symbols too. The idea is fluid. The idea is the same. If you have a $sign squared, and a $sign, that means all 3 of these have $1 sign that they could take out. Okay, if this has a pound symbol, or you may call it a hashtag, and this doesn't, and this has a pound symbol, then that means that all of them don't have a pound symbol to give up, so that's not going to show up in the GCF because this one doesn't have it. So it's just kind of helping to show you that you can do this with more than just numbers and variables. Numbers 6 and 7 are pretty simple, except I noticed that the very first term is negative. And one of the things that we learned at the top was that the first term must be positive. Close parentheses. First term must be positive, which means that if I have negative 4x squared as my first term, that means my GCF is at least going to be a negative 1, right? But the 4 and the 2 and the 8 are all divisible by 2 as well, so I can pull out a negative 2. Here, there is no GCF other than dividing by negative 1, because I don't want that first term to be negative. I can have a GCF that's negative, but I want that first term to be positive. And the last thing that I want to talk about on the front is that number 5, if you didn't divide both terms by 12xy squared, maybe you got the xy squared part, but maybe you just put like 6xy squared, that's okay, but you're going to notice that when you pull out 6xy squared, that there's still another thing that you can divide out. So I'm going to show you in pink what would happen if you divided by 6xy squared. If you divide by 6xy squared, 60 divided by 6 is 10. X cubed divided by x is x squared. Y cubed divided by y squared is y. So like my x squared y part stays the same, it's just my coefficient that's different. If I divided 36 by 6, I would have had 6 as my coefficient here, and z left over. What do you notice about 10 and 6? They're both divisible by 2. So I could divide by 2 again and bring a 2 out. 2 times 6xy squared. And what I would be left with is what I had in my answer whenever you turned your, video back on. And 2 times 6 is the 12. So if you don't see the GCF immediately, but you pull something out and then you notice that there's still something else that you can divide out, well, you can bring that out here too. Just multiply those two things back together so that you can get your true GCF. So just some helpful tips on factoring out the GCF. Let's go to the next page. The next page starts to help us answer our second essential question, which was, how do we factor using the difference of two squares? So when I say difference of two squares, difference means subtraction. 2 means like 2. There's going to be 2 of these things. And squares means like like perfect squares, like things that are squared. So it's going to end up looking kind of like this. It's two terms, it's a binomial, and it's going to have something squared minus something squared. This difference is important. If it's not a difference, then that means you can't do it. These squareds are important. If you don't have perfect squares in the first and second terms, then you can't do this. But if you do happen to have this interesting situation, then your answer will look like this every time. It will be of that form. So the first thing that you want to do always is factor out the GCF if there is one. The problem, again, must be a binomial with the two terms separated by a minus sign. That's the difference part. Both terms must be perfect squares. So you have to ask yourself, can you take the square root of both terms and get a nice pretty number? The variables with the exponents are easy to determine if they're perfect squares, but the coefficients, you have to know your perfect squares. Perfect squares are numbers like 1 squared, which is 1, and 2 squared, which is 4, and 3 squared, which is 9, and 4 squared, which is 16, and 5 squared, which is 25, and so on. So this would be a time in class when I would probably ask you, gotta make sure I get these right, where I would probably ask you if you knew your perfect squares, and if you didn't, then I would ask you to memorize them. And these show up on the diagonals of multiplication charts. So if you're used to using multiplication charts, usually in the back of your notebook, then these show up on the diagonals. So notice that if you have this format, your answer has A's and B's, but you had A squareds and B squareds in your problem. So to find A and B, you've got to take the square root of the coefficients or the constants. And the exponents need to be divisible by 2, because if you square root them, then you're really dividing exponents by 2. And finally, just check to see if you can factor any further. Always a good idea. So let's look at example 1. Let's factor out a GCF first if there is one. So 9 and 25, this is divisible by 1 and 9, 3 and 3. This is divisible by 1 and 25, and 5 and 5, right? So there are no common factors that I can take out other than 1, and that's not going to do anything. It's a binomial, check. Separated by a minus sign, check. Both terms are perfect squares, check. 25 is the perfect square when you have 5 squared. And 9 is the perfect square when you have 3 squared. And this is even, which is good. So whenever you check everything, you're trying to find A, that comes from here, square root 9x squared. That's what I need to do, square root 9x squared. What's the square root of 9? Well, the square root of 9 is 3. What's the square root of x squared? Well, the square root of x squared is x. So there's my A term. Let's talk about B. What's the square root of 25? Not negative 25, because that gives us something that we can't have, and we'll talk about that later on in the year. But just the 25. What's the square root of 25? 5. So that means that A plus B is my first part of my answer. So A plus B is 3x plus 5. And the second part is A minus B. So 3x minus 5. And I can't factor anything out further, so this would be my answer. All right, let's look at number 2. Number 2, there's no GCF to take out. It's a binomial. There's a minus sign. 4 is a perfect square. X squared is a perfect square. What's the square root of 4? What's the square root of x squared? When you square root a square, that just kind of goes away and you have x. So my answer would be A plus B, so 2 plus x, times A minus B, 2 minus x. There. All right. Let's look at number 3. 50x squared minus 2. I notice that both of those, well, neither of those are perfect squares, but I notice they're both divisible by 2. So if I let a GCF of 2 sit out here, 50 divided by 2 is 25. That is a perfect square. So is x squared, and so is 1. So what is the square root of 25x squared? Square root of 25 is 5. Square root of x squared is x. What's the square root of 1? That one's easy. 1. So my answer still has a GCF of 2, but it's of the form a plus b, so 5x plus 1, times a minus b, so 5x minus 1. Cool. All right. Let's look at number 4. Definitely have a GCF because 2 is something I can take out. I also notice that they both have a y. I'm going to take out a y as well. 2y. 2's cancel out. Y's cancel out. X squared remains. That's a perfect square. Minus 162 divided by 2. If I take 16 and I cut it in half, that's 8. 2 cut in half, that's 1. The y cancels out. 81 is a perfect square. So we have a GCF and we have a difference of 2 perfect squares. What's the square root of x squared? X. What's the square root of 81? 9. So I still have the GCF of 2y, but then I also have x plus 9 and x minus 9. And by the way, we've talked about how like the square root of 81 is 9 and the square root of 1 is 1. The square root of 4 is 2. Or I guess here the square root of x squared is x. The square root of 25 is 5. Now when you take the square root of a number, you don't just get the positive value. You get the positive and you get the negative, which is why you have a plus 5 and a minus 5. Square root of 1 is not just 1, it's positive and negative 1. So we have a plus 1 and a minus 1. Square root of 81 is a positive 9 and a negative 9. So we have a plus 9 and a minus 9. So just kind of throwing that in there because I think it's helpful to you. Now the last page has 6 examples. I'd like for you to pause your video and try as many as you can. I will have the answers up there for you in just a moment. Pause your video and try them out. Here's 5, 6, 7, and 8. Notice that whenever you square root a term that has an exponent that's even, basically you're taking those exponents and you're cutting them in half. So keep that in mind. It's the only really extra thing that's happening in these problems. I also noticed that number 8 was not a difference problem, but whenever you take out a GCF of -1, it did become a difference of 2 squares. And then finally, here are the answers to 9 and 10.